Good afternoon, everybody. Welcome back to lecture number
4.
4. That is correct. When do you want us to assign the major exam dates?
عندي صغير من المناجر بدري أنا
After the schedule is released? Okay. Do you want your major one to be before or after? Before the official period begins?
حسب الماتيريال لسه بس تشد الماتيريال اللي فقطه.
I write my major exams usually 2 hours before the majors. Doesn't matter. طيب. Did you review the synchronous generators?
لا دكتور عندك نسخة PDF للكتاب؟
I have a PDF version, but it's not clear. Okay, remind me in Teams to upload the books, okay? Just send me by Teams, because I forget sometimes. طيب, we have issue with the monitor here.
تطفيه وشغله.
It's not responding.
خليك ضارب على زر الباور لين تطفي.
Restart?
ريستارت.
No, it's... هو الويندوز اللي معلق مو الشاشة. طيب. So let me begin. Last time we talked about what? The exciter. And what did I tell you? Remember, we in this course we do nothing but block diagrams. They're very important. In the exciter, what we had here stator, we had here the rotor. So the first step is to apply
A 3-phase or small 3-phase.
not the pilot, the regular one, small
AC.
3-phase AC. And then here you do
Rectifier.
DC to AC ولا AC to DC, AC to DC converter. Then you apply it on the field circuit, صح?
صح.
In the field circuit, it would induce in the rotor what? AC. That's why we have 3 phases, 3 windings. Each one of them would have an induced voltage that's 120 degrees apart. Okay? Then we got the excitation thing done? No, not yet. We have to convert it back from AC to
DC.
DC and then apply it on the field. Now it's rotating and now it will induce what?
3-phase.
3-phase. Your 3-phase out. Get it? Now the pilot is nothing but this small component is actually deleted and you get it through 3-phase windings whose excitation is using what? The pilot. What's the pilot? Small PM. PM يعني permanent magnet. When the permanent magnet rotates, it induces a voltage here. Okay? Look at the original block diagram. Now, how to deal with this?
شوف تحت الزاوية الويندوز. زاوية يسار.
هنا.
اوكي زاوية يسار.
Okay, what else do we have? We talked about the synchronous speed, correct?
1.10 over 4.
And what was the formula? The formula was NS is 120 F over P, correct? And we talked also about the induced voltage, EF. And what was the formula? 4.44 times flux, speed, N windings. We said these two are not in this course. The only thing you have control is either the flux or the frequency. Okay? What else we talked about? Manish, I'm so sorry. What's happening here is I know it's not updated. Well, it turns out it is updated. Okay. So what else we talked about? We talked about the importance of noticing the clear relationship between the frequency and the induced voltage. If you want to change the frequency of your generator, you have to change the mechanical speed that you're rotating at. So this is what we talked about last time. And it has to be synchronized all the time. Without synchronism, synchronous generators are useless. That's why for the wind turbine we use induction generators because we cannot synchronize the wind. But for fossil fuel power plants, we are synchronizing it all the time. We have tools of synchronism that ensure that frequency is always under control. And I told you last time that either F or the flux, if you change one of them or both of them, you can either increase or decrease the amount of induced voltage. Induced voltage. The EF occurs when this winding that has DC, that's excited by DC, rotates and generates three-phase output on the synchronous generator. Now, we are limiting our discussion in this course, or at least in this module, mainly toward synchronous generators. Okay? Why? Because they are more useful. Synchronous motors are useful, but they are mainly with permanent magnet. We don't need exciters for them. You're familiar with these shapes in E360, delta Y connection. But let's look at some math. Let's look at some analytical derivation of the rotating magnetic field. We always begin with what? Begin with IA, IB, IC. They are 120 degrees apart. What will happen if you add IA plus IB plus IC? The summation is 0. If you don't believe me, try any number cosine of 0, angle 0, plus minus 20, plus minus 240, or plus 120, they are the same. If you add all of them in a balanced system, they are 0. Now, the MMF, the magnetic motivated force, if you add A and B and C, you get the resultant one. But are they 0? Not really. Why? Because the MMF of phase A is NIA cosine theta. Note that IA has a cosine omega t, while the MMF has cosine theta. If you do, and the other one is minus 20, the other one is plus 20. These thetas have to do with the current position of the rotor. It's the electrical angle If you have a two-pole machine, electrical angle is same as mechanical angle. If you have a 4 or more pole machines, electrical angle is divide them by number of poles. What I mean is, I'll explain it later, but what I mean is that when we look at, in machines, when we look at electrical degrees versus mechanical degrees, they are completely different. Mechanical means on the structure. If you have two poles, 360 degrees is all the way across the mechanical structure. But if you have 4 poles, going 180 mechanical degrees is equivalent of going 360 degrees electrical. If you have 8 poles, the quarter of the mechanical part would cause full electrical. Get it? You don't get it? So, in order for, you have a stator, صح? And you have what? A rotor. At the beginning, this is the axis of the stator, and this is the axis of the rotor. Let's do it in this color. When the rotor spins, let's say we have 2 poles. If we have 2 poles, it means anything here is north, anything here is south. So we have north and south. So if you make full rotation, that's what? 360 or 2 pi. If you have north-south and north-south, if you rotate half, it's electrical 2 pi. Now, add more poles. You have here north, south. You only need to rotate number of poles divided by, 360 divided by number of poles. Here we have 6 poles, or 3 pole pairs. So divide them by 6. So that's the only thing that you need to constitute one electrical route. Having said that, for big synchronous generators, a small movement of the rotor would consider will generate full sinusoidal cycle. Get it? For synchronous generators, because they have 20 poles or 30 poles, a small mechanical rotation would guarantee for you a full sinusoidal electrical output. That is what we mean by electrical degrees versus mechanical degrees. And I think the formula theta of electrical is what? Theta of mechanical divided by number of poles. Is it P over 2? We'll come to it later, but I think it's just divided by number of poles. What matters is the understanding, is that you don't need for rotation for that to occur. Now let's go back to the analytical derivation. Multiply IA, substitute the IA and the IB and the IC with this mathematical term. You would get NIM cosine times cosine plus NIM cosine times cosine plus NIM cosine times cosine, and turned out they are in this form, A and B. We can use A and B. We subtract A and B, then we add A and B. This is math 002. If you do the math, you will end up with having 6 terms. Now here we have, how many terms we have? 1, 2, 3. Each one would be split into 2 terms, so we're going to have 6 terms. The terms that have omega t minus theta, omega t minus theta, omega t minus theta are the same. And we call them the forward rotating components. They are forward rotating components. They do not cancel each other. While the other 3 terms, they are, if you add them, the backward rotating components, if you add them, you're going to end up with 0. Okay? If you do the math, you'll get these numbers. So your component is half plus half plus half is 3 over 2 NIM cosine omega t minus theta. So the resultant MMF at any point of theta is 3 over 2 NIM cosine omega t minus theta. Okay? This may answer the question is why we always have a 3-phase. If we have a rotor rotating on 3-phase winding machine. So any question about slide number 10?
Doctor, just to clarify, the cosine theta for the MFF is where did it come from? We have cosine for the current, we have cosine WT, correct?
This one?
Yes. What does it represent?
So this represents if the rotor, for example, is at this location. That's not good. You have a stator and you have a rotor, and the rotor north and south has its own, it's already excited, it has its own poles, is theta degrees away from the stator north. This is theta. If you change it, you're gonna change the MMF. Sometimes you get the peak at this location. So, no, that's south, north. So the lines go from north to south, correct? If you have your south pole this way, you are 90 degrees. So your magnetic lines will look that way. Every time they rotate, the magnetic intensity changes because the MMF changes. The theta is somehow the peak of the magnet of the rotor. This magnet is fake. We generated it using excitation. With the original north and south stator magnets, the magnetic flux lines will change every time. So this theta would govern the peak, the zeros, etc. of every magnetic flux line for every set of windings, A or B or C. If you add all of them, you're going to have this equation, which is 3/2 NIM cosine omega t, where omega has to do with 2 pi f, the mechanical, how fast your synchronous machine is moving, and theta is where is the location of your north and south poles of the rotor. Now, if you have more than one pole, 2 poles, like if you have 4 poles, you're going to have different north and south in the rotor and the stator. So we're adding everything up. Okay? So theta has to do with your mechanical reference or mechanical angle. So any question? You don't need to know the details for now. We're going to explain it. But for now, understand that cosine theta minus 20 has to do with where your windings are inserted, the physical location of them. Now, we all remember this synchronous generator or synchronous motor curves. Do you remember them?
Physics, yes.
The power?
There you go. Power losses.
Let's look at synchronous generator. What's our input?
The torque and applied.
Torque and speed, not only torque. You apply torque
Speed.
at a certain speed. And usually this speed has to do with number of poles and the frequency that you want. We're going to have stray losses, friction, core losses, and here we have what we call the air gap power that crosses from the stator to, that crosses the rotor to the stator. So anything here before has to do with
The rotor.
the rotor. After friction with windage, etc., it goes all the way to the stator. So it crosses the air gap. We're going to have I square R losses, copper losses in the windings of the stator. Then we will have our output square root of 3 VL IL cosine theta. These are line-to-line quantities because in power system, we always deal with line-to-line quantities. Keep in mind that for the synchronous motor, the opposite is true. Here they're using terminal quantities, phase quantities. That's why there is no square root of 3. 3 VT IA cosine theta, that's our input, electrical. Then we have the reverse power losses. At the end we get torque and speed mechanical. So that's a synchronous motor. Efficiency is usually calculated by output over input. Output over input. So any question that has to do with efficiency, you need to divide output over input. This is just a review, not really important. You remember the equivalent circuit of a synchronous machine? Yes, we have EF, which is the field excitation voltage. Then we have synchronous reactance, XS. Usually when you do circuit analysis, don't forget to add J. Don't forget to add J. And then we have RA, which is the armature resistance. Sometimes we ignore the armature resistance. And then you have the V terminal. So what's the formula? The formula is if you do KVL, voltage rise, EF, equal VT plus IA times RA plus JXS. Sometimes we refer to it as EF at an angle delta. This delta angle is what we call it the power angle. Sometimes we call it the... Oh, did we record? Yeah. Please check the recording. This is power angle. Sometimes we call it what? The torque angle. Basically, this angle is the angle of the rotor, electrical angle of how the rotor south pole deviates away from the stator north pole. If they are in line, you're going to induce the voltage in phase. EF will be in phase with the terminal voltage. The moment it deviates, it will always deviate, which we call it synchronism. If it deviates, it's not the angle of the rotor itself, the magnetic flux angle. If it deviates from the stator, that's what we call it delta. Let me explain. It's same concept. You have the rotor. This spins all the time, right? However, you have to draw a magnetic field, magnetic axis. Here we have another magnetic axis, okay? Here, is the deviation of the magnetic axis of the stator versus the magnetic axis of the rotor. Now, the magnetic, how can I explain it? The rotating magnetic field is uniform, correct? When the rotor spins, we have to make sure that we synchronize that delta to be fixed. Otherwise, this delta will deviate. It spins all the time, but the magnetic flux, we control it in a way that everything rotating, هنا عندي AC, this is rotating. So, delta has to be fixed so that we can have synchronized output. How to do synchronization, we'll go over it. But think of it that way. Think of it as I have a machine that is spinning. Magnetic flux has an axis. Stator has an AC generated. It has its own axis. I have to control that delta, which is the angle between the two axes. Yeah, this rotates all the time. But the magnetic flux, when it rotates, everything rotates with time. Get it? That delta has to be maintained. If I decrease it or increase it, we will see what will happen.
slip صار induction صار.
No, ما هو slip. Has nothing to do with the slip.
صار في إذا كان الروتور
No, slip
مو
has...
synchronized مع magnetic field بصير في induction motor صار.
Yeah, but slip has to do with the actual rotor movement. Delta has to do with how fast the magnetic flux line is rotating. يعني at a certain snapshot of time. This is the rotor. This is the stator. North, south, south, north. This is the air gap, okay? This is north to south, north to south.
الحين هذه الدلتا زيرو.
For now. Then this rotates. لا هنا ما في شيء. هنا في set of windings. When this rotates, these magnetic flux lines, the poles will change their locations. The poles will change their location. At another instant of time, the north peak will be here. South peak will be here. Now here delta is 0. Here delta is 0.
الحين هذا synchronous machine.
لا ايوه هي synchronous machine بس what I'm telling you is if you have a certain delta already انت from the beginning is south هنا والnorth هنا. Already you have deviation of the axis. فthey rotate over time. معناته الnorth هنا والsouth هنا. They rotate over time. This delta is greater than 0. Because everything is AC, the poles are rotating over time. Yes.
So it should be constant value.
Yes, it has to be constant. Otherwise, your output will not be uniform in the synchronous generator. Okay?
slip related to the speed.
السليب هذا في الانduction machine الروtation goes up and down. Synchronous, the prime mover has to rotate at the exact synchronous speed.
Okay.
What's changing is the magnetic north والساوث حقت الستيتر والنورث والساوث حقت الروتر. If they are aligned, delta is 0. If they are not aligned, there is a delta. But over time they rotate with each other. النورث والساوث يغيرون أماكنهم. Get it?
Okay.
It's hard to visualize, but get it as it is right now. For a synchronous motor, the only thing you change is IA has to go from the terminal to EF. If you change the polarity, the only thing that will change is these pluses will be minus and your delta will become a negative number. Delta will become a negative number. Let's look at phasor diagrams. The first case is we have lagging power factor. Okay? What lags what? IA lags VT by an angle of theta. You see, this is IA, this is V. This one is lagging. The second curve is unity power factor. IA is in phase with V. The third case is leading power factor. IA leads V. So when we talk about lagging, leading, unity power factor, we compare IA with V terminal. Why? Because there's those two quantities that I have access to in my circuit. T terminal, I have access to the terminal voltage, and I have access to the armature current. If I connect a load here, by knowing IA and VT, I know whether the load is lagging or leading or unity power factor. If I connect a pure resistor here, VT and IA will be in phase. If I connect an inductive load, IA would lag VT. If I connect a capacitive load, IA would lead VT. So the first thing in the phasor diagram is you have to notice what's the relationship between IA and V. IA and V. V is VT. IA and VT. The second thing I need to know is I need to apply this equation for a synchronous generator to calculate EF. Here we put it E. E. In all of the three cases, delta is positive, delta is positive, delta is positive, where delta is the angle between EA and the reference. What is my reference here? My reference is VT, because it's at an angle 0. So I'm measuring how much EA is deviating from VT. It turned out that delta, the magic number, is the same as the number that when you start spinning your machine, the magnetic flux lines are different. Okay? By delta. Let's continue. How to read these phasor diagrams? Yes?
So we don't aim to make delta 0. Right?
No. Delta is the torque angle. It has to do with the synchronization of your synchronous generator. طبعا it has to do with the torque, and too many other. Even the loading conditions would change delta. If you add bigger loads, delta will change. Delta is the angle between E and V. E and V, E and V. In all cases, for the synchronous generator, torque angle or power angle is positive. That's one thing. Another thing I need to know is to get the E, I need to get Vt plus IARA. This small arrow is IARA, small arrow is IARA, small arrow is IARA. Note that we just scale the IA with the number RA. Usually RA is a small number, so that's why the arrow is smaller. The last quantity is J, which is 90 degrees, IAXS. So scale IA with XS and add to the angle of IA another 90 degrees. So in this case, IA here, add 90 degrees, so it will be here. This is vector addition. For the unity power factor, IA is in phase with V, so the 90 degree will be right triangle. The last one, IA is leading, so JIA times XS will be a little bit more than 90 degrees.
طيب دكتور الحين وش فائدة هذه الباور انجل؟ هل إذا زدتها وش الإفكت بيصير على الماشين؟ إذا زادت أو قلت؟
This power angle has to do with the stability of the machine, has to do with the power that is being delivered to the load. If you remember in 360 we had this equation before. Do you remember this equation?
أيوه.
So if you change delta, you change power. The highest power is if delta is 90 degrees. You get the maximum power. With this term. But the thing here is, if you change delta, EF magnitude will also change. And that's what we are studying here. Because in 360, we just memorize the equation. In 462, we would derive the equation. But delta has to do with power. That's why we call it power angle. Of course, if you increase the power, you increase the torque. So we also call it torque angle. It has different names. Let's look at again the phasor diagram. In all of the three quantities, if you do the projection across cosine delta, EA cosine delta, you'll get this number, Vt times IARA. So if you do the projection here, EF times cosine delta, if you multiply it, you would get the same number as V plus IARA. If you do the projection, for the normal excitation. So this is normal excitation. For the lagging power factor, is it what? Lagging is what? This is over excitation. This is what? Under excitation. For the normal excitation, if you do the projection EA cosine delta, it goes over V plus IARA. That's for the normal excitation. For the over excitation, we are overly exciting the machine. Under excitation, E is under excited. So if you have lagging, unity, and leading. For the normal excitation, what is the is V larger, magnitude larger than E in the overexcitation? No. E is larger. For the normal excitation, is E larger than V? No, it is larger. Yeah, that was your mistake in the final. It's positive. Voltage regulation is positive. EA is still positive. For the under excitation, EA sometimes becomes smaller than V. For the under, that's why you have a negative voltage regulation. It's under excited. We will solve examples, so don't worry. Right now I want you to try to get the new concepts along with revision of 360. For the synchronous motor, delta is always negative. So if you find your E's at the bottom, you're in the motor. If you find your E's on the top, you're in generator. We do the same equation. So delta here is a negative number, yet he is posting it like the slides, he's writing it negative delta, but in your calculation, delta is a negative number. So you can say this is positive, but you have to state delta is already a negative number, because this is a negative number. Or you can say delta is a positive number.
حط ماينس نفس
لا تحط ماينس. delta is a positive number هنا يعني هنا تحط يا minus 30 ولا 30. You can put 30 و keep النيجاتيف هنا. الفكرة إنه ال EF has a negative angle all the time. Let's continue. For the leading power factor, we flip everything. So the leading power factor is overexcitation. Where is the leading? This is the leading. Here we have leading. Don't confuse yourself. This is leading. Overexcitation. Normal excitation. Lagging will become what? Underexcitation for the synchronous motor. So remember, for lagging, for generators, we have overexcitation. For motors, lagging will be what? Underexcitation. Opposite is for leading. Leading for the synchronous motor is overexcitation. Leading for synchronous generator is underexcitation. And a unity power factor is always normal excitation. Now, we talked about, any question about the phasor diagrams? I think they are clear, correct? Are they clear?
Yes.
So again, what is delta? Power angle, also known as the torque angle. And it has to do with the deviation of the flux lines, the peak of the flux lines between the rotor and the stator. Keep in mind, if this spins at 60 hertz, the whole thing would spin. It's not delta will change over time. Delta will change if you demand more power. If you add more torque to your machine, delta then will change. Now we have the parallel operation of synchronous generator. Why do we have synchronous generators operating in parallel? Why sometimes we have G1 and then we have G2 and then we connect them to the line? For reliability. If one generator dies, the other one is still running. Also for economic operation. Sometimes it's cheaper to build two smaller generator power plants than having one giant power plant. That's one other application. But here is the thing. You are not allowed to connect two generators in parallel unless you have these conditions. We covered them in 360, correct? They need to have same voltage, same frequency, same phase sequence, and same phase shift. Phase sequence يعني كلهم ABC, not ACB. And how to do this in real life? Did you do it in 361? The synchronization?
No.
Okay, if you're taking the lab, I think you're going to have one experiment about synchronization. So how to do it is very simple. Assume generator A is already connected to the line. Here we call it infinite bus. You first connect 3 different light bulbs. And these light bulbs, they would be on. You connect your generator to the light bulbs to the line. When the light bulbs turn off, you connect the switches, and this is synchronization. Get it? Why they are off? Because if they are off, the line frequency will be same as generator B frequency. If they are in the same frequency, this will be short circuit. If it's short circuit, there is no voltage applied on the lamp. If there is no voltage applied on the series lamps, they will turn off. If they turn off, it means the voltage generated from generator B, VB, same as VL. That's why when our light bulbs are off. Now I can connect the breakers and forget about the light bulbs. You will do this in the lab. So here we have EA, capital B, capital C. These are the voltages for A, B, and C, the line or the infinite bus. The small letter is for the incoming machine. EA, this is capital A minus small a, which is basically the voltage drop between capital A and small a, is the light bulb 1, light bulb 2, light bulb 3. Initially, without synchronization, there is a voltage drop, so all the light bulbs will be flickering. If all the light bulbs turn off, it means I am in synchronization mode and I can safely close all the breakers. So question in the test. In the synchronization process, I have to wait until
Light turn off.
all the 3 light bulbs are off. So synchronism is very important. There are many control methodologies to drive the motors into synchronization. So the power grid is like an infinite pool. If a synchronous generator tries to connect without synchronism, this synchronous generator would probably be driven out of the system and it will be damaged, but the grid will not be damaged because the grid is infinite bus. So be careful when you connect generators. You will do an experiment if you're taking the lab. Who is not taking the lab? Okay. You graduated. Your lab is real life. Okay, synchronization process. That's what you need to know. Now let's see, for example, what will happen if you change the frequency. If you start from the same, all the phasors, they are in line, after some time, you will notice that the phasors would be deviating away. So for example, EA, which is the infinite bus, E small a is the incoming machine, they will have a voltage drop. You see these arrows? These arrows are the ones, the small arrows, ECC, EAA, EBB. If we have synchronized, these are the voltage across the light bulbs. If they are there, then the light bulbs will be flickering. If they are synchronized, if the frequency is the same, this arrow will be 0. So they need to have the same frequency. What this implies? This implies that both rotors of A and B, they should rotate at the same RPM. Okay? Another thing is different phase sequence. What is phase sequence, for example? One is A, B, C, the small letter. The capital letter is A, C, B. They are not in the same phase sequence, so those diagonal arrows will exist. Keep in mind, this is a very big one. This is a big one. This is a bit smaller. A, B, C versus A, C, B. Another thing is, if I have a different phase shift. If I have a different phase shift, even if I have the same frequency, I'm going to still have a deviation between the small a and the capital A, the small c and the capital C, and the small b and the capital B. All of them would make the lights flickering. Get it? So synchronization is a very important thing in terms of the machines. Another thing we have to talk about is the finding the values of synchronous reactance. Most of you did do this open circuit test. Did you do it all? So open circuit test, the synchronous machine is driven at synchronous speed. The terminal voltage is open, so Vt equal to EF, and we measure the field current. We vary the field current. The field current is in the rotor, the exciter. The curve showing variation of EF, IF, they are known as open circuit characteristics. For example, they look like that. This is the curve, OCC. You start with 0 IF, your EF is 0, and then you draw the curve in the lab. This is open circuit characteristic. The line passing the tangent line in the linear part is called the air gap line. This is the air gap line. The tangent of the linear part is the air gap line. The modified air gap line is the one that is a little bit more toward the knee, that cuts the knee. هذا المodified air gap line. So we have air gap line, we have the modified air gap line. So the excitation voltage would have changed along this line if there were no magnetic saturation effect. But because there is a saturation, we need to have a modified one عشان السaturation, to accommodate the saturation. For the short, now how to do it? You measure the EF, you measure IF, and then you draw the OCC. For the short circuit, we short circuit A and B and C together. We tie them together using ammeters. Synchronous machine is driven again at the synchronous speed, rated synchronous speed. We vary the field current. 3 armature currents are measured. The variation of armature current with the field is known as the short circuit characteristics. How it looks like that. So here we have the current. We have a double y-axis. Here for EF, and here for the current, the armature current, IA. And then we plot this line. Then what will happen is, for the short circuit, we don't need to worry about saturation, because even if you change the field excitation, even if you change IF, your EF is never reaching the saturation. It's here. This EF is low for a short circuit, so you don't need to have a modified line. You just use SCC. And then you use the equation. You have to decide, are you in the unsaturated mode? Do you want to get the excess that is not saturated? We have 2 reactances. One is saturated. Okay, time is up. We'll continue next stage. Okay? So we'll start next lecture. Any question? Thank you.